Hello, this is my Standard 7 assessment. I chose problem 7.31 from Classical Mechanics by Taylor, and it's a pendulum mass m and length L is suspended from a cart mass m that can oscillate on the end of a spring constant k as shown in figure 7.15. Part A is write the Lagrangian in terms of the generalized coordinates x and phi, where x is the extension of the spring from its equilibrium length. Find the two Lagrange equations. Simplify the equations to the case that both x and phi are small. So I wrote the diagram at the top, and then we know the velocity of the cart is just x dot, and the kinetic energy is just 1/2 mx dot squared. The kinetic energy is just 1/2 kx squared for the spring constant, and then the position of the cart is x plus L sine theta x hat minus L cos phi, these are phi's, y hat, and then we have to take the derivative of that to get the velocity, and we square it. And after we square it, we plug it in. After we square the velocity, we plug it in for the kinetic energy to 1/2 m, and then this is v squared, so we put that in here. And then the potential energy is just gravity, and it's mg, and then the L cosine phi for that component. And then we sum the kinetic energies up of the cart and the mass, the pendulum. Then we sum the potential energies up of the spring and gravity. Then we write the Lagrangian. Whenever I wrote the Lagrangian, I realized that you could factor out L squared phi dot squared to get cosine squared phi plus sine squared phi, which comes to 1. So it makes it a little easier. So I rewrote the Lagrangian, and then I need to take the time derivative with respect to L dot, and I did that in this step. So once I get the time derivative with respect to L dot with respect to x dot, I need to get the partial derivative of L with respect to x, and then I need to set them equal to each other to get the equation of motion. So that's equation 1 with respect to x, and then I need to get the time derivative with respect to phi dot, and then I get an equation, and I have to next get the partial with respect to phi. I get another equation. I set those equations equal. And it turns out the m's and most of the l's cancel out. So then I need to take into account that phi is very small and x is very small. So for equation 1, I get negative kx equals m plus m x double dot plus ml phi double dot minus ml phi dot squared phi. And then for the second equation, I get negative g phi minus x double dot plus L phi double dot. That's supposed to be a phi. And the equations simplify a lot more after you take into account that phi and x are pretty small.